Theorem number 3. Theorem number 3. The harmonic series sigma 1 upon n is equal to 1 to infinity is divergent. Is divergent. Proof. We have the series sigma 1 upon n. We have the harmonic series summation 1 by n is equal to 1 to infinity 1 upon n, which is equal to 1 plus 1 by 2 plus 1 by 3 plus and so on plus 1 by n plus and so on. Let Sn is equal to S suffix n is equal to 1 plus 1 by 2 plus 1 by 3 plus and so on plus 1 by n. For all n belongs to I, for every positive integer n. Let Sn is nth partial sum of series sigma 1 upon n is equal to 1 to infinity. S1 is equal to 1. Sum of first term, that is S1. S1 can be written as S suffix 2 raised to 0 is equal to 1, which is equal to 2 plus 0 upon 2. 2 plus 0 upon 2. S suffix 2 raised to 0 is equal to 1, that is S1 is equal to 2 plus 0 upon 2. S suffix 2 is equal to sum of first two terms 1 plus half. Sum of first two terms, that is 1 plus half, which is equal to 3 by 2. 3 by 2. S suffix 2 to the power 1, that is S2, is equal to 2 plus 1 upon 2. 2 plus 1 upon 2. S suffix 2 raised to 1 is equal to 2 plus 1 upon 2. S suffix 4. S suffix 4 is equal to sum of first four numbers, that is 1 plus half plus 1 by 3 plus 1 by 4. Sum of first four terms is equal to this is S2. S1 is 1 and S2 is 1 plus half, that is 3 by 2. 3 by 2 plus 1 upon 3 plus 1 by 4. But 3 is less than 4. 3 is less than 4. Therefore, 1 upon 3 is greater than 1 by 4. Therefore, we write S suffix 4 is equal to 3 by 2 plus 1 by 3 plus 1 by 4 is greater than or equal to 3 by 2 plus 1 by 4 plus 1 upon 4. 1 upon 4 plus 1 upon 4 is 2 by 4, which is equal to 2. S suffix 4 is greater than or equal to 3 by 2 plus 2 by 4, which is equal to half. 3 by 2 plus 1 by 2, which is equal to 4 by 2, which is equal to 2 plus 2 upon 2. S suffix 4 can be written as 2 to the power 2, which is greater than or equal to 2 raised to 2 is greater than or equal to 2 plus 2 upon 2. Similarly, we write S suffix 8. S suffix 8 is equal to 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8. Sum of first 8 terms of the given series. Sigma 1 upon n. S suffix 8 is, this is 1 plus half plus 1 by 3 plus 1 by 4 is S4. S suffix 4 plus 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8. 1 by 8. But 5 is less than 8. 5 is less than, but 5 is less than 8. Therefore, 1 upon 5 is greater than 1 by 8. 6 is less than 8. Therefore, 1 by 6 is also greater than 1 by 8. Again, 7 is less than 8. 7 is also less than 8. 7 is less than 8. Therefore, we write 1 by 7 is greater than 1 by 8. Therefore, S suffix 8, S suffix 8 is greater than or equal to, S4 is greater than or equal to 2, 2 plus 2 upon 2, that is 4 by 2 is 2, is greater than or equal to 2 plus 1 by 5 is greater than 1 by 8. 1 by 6 is also greater than 1 by 8. 1 by 7 is also greater than 1 by 8. And 1 upon 8 is equal to 1 upon 8. Which is equal to 2 plus 4 by 8, which is equal to 2 plus 1 by 2, which is equal to 5 by 2, 5 upon 2. S suffix 8 can be written as S suffix 2 raised to 3, which is greater than or equal to 5 by 2. 5 by 2 can be written as 2 plus 3 upon 2. And so on in general. And so on in general. We write S suffix 2 raised to n. S suffix 2 raised to n is also greater than or equal to 2 plus n. 2 plus n upon 2. For all n is equal to 0, 1, 2 and so on. For every n is equal to 0, 1, 2, 3 and so on. Limit n tends to infinity of S suffix to n. Now, limit n tends to infinity of S suffix 2 raised to n is greater than or equal to limit n tends to infinity of 2 plus n upon 2, which is equal to, as n tends to infinity, limit limit of 2 plus n upon 2 is also equal to infinity. Therefore, the sequence s suffix 2 raised to n is equal to 0 to infinity, diverges to infinity. This sequence s suffix 2 raised to n is equal to 0 to infinity, diverges to infinity. But s suffix 2 raised to n is equal to 0 to infinity is a subsequence of Sn, n is equal to 1 to infinity. But s suffix 2 raised to n is equal to 0 to infinity is subsequence of sequence Sn, n is equal to 1 to infinity. 1 to infinity. N is equal to 1 to infinity. And this sequence, this subsequence diverges to infinity. Therefore, sequence Sn n is equal to 1 to infinity diverges to infinity. Therefore, sequence s suffix n is equal to 1 to infinity diverges to infinity. Therefore, by definition of divergence of series, corresponding harmonic series sigma 1 upon n is equal to 1 to infinity is divergent. By definition of divergence of series. By definition of divergence of series, sigma n is equal to 1 to infinity, 1 by n is divergent. Hence the proof of the theorem. Hence the proof of the theorem. Theorem 3. Example. Prove that 1 plus 1 by 2 factorial plus 1 by 4 factorial plus 1 by 6 factorial plus and so on converges. Prove that this series 1 plus 1 upon 2 factorial plus 1 upon 4 factorial plus 1 upon 6 factorial plus and so on converges. Solution of this problem. Let Sn is equal to 1 plus 1 by 2 factorial, 1 upon 4 factorial, 1 by 6 factorial, plus and so on 1 upon 2 into n minus 1 factorial for all n belongs to I, for every positive integer n. If we put n is equal to 1, we obtain 0 factorial is 1, n is equal to 2, 2 minus 1 is 1, 1 into 2 is 2 factorial. If we put n is equal to 3, 3 minus 1 is 2, 2 into 2 is 4 factorial. If we put 3, 3 minus 1 is 2. If we put 3, we obtain 3 minus 1 is 2 into 2 is 4 factorial. If we put 4 4 minus 1 is 3, 3 into 2 is 6 factorial, and so on. This is S suffix n. Therefore, S suffix n plus 1 is equal to 1 plus 1 upon 2 factorial, 1 upon 4 factorial, 1 upon 6 factorial, plus and so on, plus 1 upon 2 into n minus 1 factorial, plus 1 upon 2n factorial. For every n belongs to I, for every positive integer n. S suffix n plus 1 minus Sn. Now, S suffix n plus 1 minus Sn is equal to 1 upon 2n factorial for every n belongs to I. For every positive integer, n belongs to I. As n tends to infinity, 1 upon 2n factorial becomes 0. Becomes 0. That is, S suffix n plus 1 minus Sn. S suffix n plus 1 minus Sn is equal to 1 upon 2n factorial, 2n factorial, which is greater than or equal to 0 for every n belongs to I. That is, S suffix n plus 1 minus Sn is non-negative. Non-negative, greater than or equal to 0. Sn plus 1 is greater than or equal to Sn for every n belongs to I. For every positive integer, n belongs to I. That is, Sn is less than or equal to Sn plus 1 for all n belongs to I. If we put n is equal to 1, we obtain S1. S1 is less than or equal to S2. If we put n is equal to 2, we obtain S2 is less than or equal to S3. If we put n is equal to 3, S3 is less than or equal to S4, and so on. Sn is less than or equal to Sn plus 1 and less than or equal to, and so on. Therefore, by definition of monotonic sequences, sequence Sn n is equal to 1 to infinity is 1 to infinity is non-decreasing sequence. Non-decreasing sequence of real numbers. Sn is non-decreasing sequence of real numbers. Now, this is a statement number 1. Statement number 1. Now, Sn is equal to 1 plus 1 by 2 factorial, 1 upon 4 factorial, 1 upon 6 factorial, and so on, plus 1 upon 2 into n minus 1 factorial. Factorial. This is equal to 1 plus 1 by 2 plus 1 upon 4 factorial is 1 into 2 into 3 into 4. That is 1 by 3 into 1 by 4 in 1 half into 1 half into 1 by 3 into 1 by 4, 1 upon 2 into 1 upon 3 into 1 upon 4. Next term, 1 upon 1 into 1 half into 1 by 3, 1 by 4, 1 by 5, 1 by 6, and so on. And so on. Last term is 1 upon plus and so on, plus 1 upon 2 into bracket n minus 1 factorial. Factorial. For every n belongs to I. For each positive integer, n belongs to I. For every n belongs to I. Belongs to I. But 3 is greater than 2. 3 is greater than 2. Therefore, 1 upon 3 is less than 1 by 2. 3 is less than, clearly 3 is greater than 2. Therefore, 1 upon 3 is less than 1 by 2. 4 is greater than 2. Therefore, 1 by 4 is less than 1 by 2. 5 is greater than 2. 1 upon 5 is also less than 1 by 2. And so on. And so on. Therefore, this Sn, S suffix n, can be written as less than or equal to 1 plus 1 by 2 plus 1 by 2 into 1 by 3 is replaced by 1 half. 1 by 4 is less than 1 half. 1 upon 2 into 1 upon 2 plus 1 upon 2 into 1 upon 3 is replaced by 1 by 2 into 1 upon 2 into 1 upon 2 into 1 upon 2 plus and so on. Last term is 1 upon 2 into n minus 1 factorial Sn. S suffix n is less than or equal to 1 plus 1 by 2 plus 1 upon 2 raised to 3 plus 1 upon 2 raised to 5 plus next term is 1 upon 8 factorial. Next term will be 1 upon 2 raised to 7 plus and so on. Last term is plus 1 upon 2 to the power n minus 2 raised to n minus 2. Sn is less than or equal to 1 plus addition of all these numbers, half plus 1 upon 2 raised to 3 plus 1 upon 2 raised to 5 plus 1 upon 2 raised to 7 and so on. First term is 1 half, 1 upon 2. Common ratio is 1 upon 4. A into 1 half into bracket 1 minus common ratio 1 upon 4 raised to how many terms? Raised to n minus 1 terms upon 1 minus common ratio is equal to 1 plus 1 by 2 into bracket 1 minus 1 upon 4 raised to n upon 3 by 4 upon 3 by 4. This is a square bracket is 1 minus 1 upon 4 raised to n minus 1, which is less than 1. Therefore, Sn is less than 1 plus 1 by 2 into 1 upon 3 by 4. 3 by 4, which is equal to 1 plus 1 by 2 into 4 by 3 into 4 by 3, which is equal to 1 plus 2 by 3. 2 by 3, which is equal to 5 by 3. Therefore, sequence Sn is less than 5 by 3 for every n belongs to I. Sequence Sn is equal to 1 to infinity is bounded above 1 to infinity is bounded above. This is said too. But we know a theorem a non-decreasing sequence which is bounded above is convergent. But we know theorem, a non-decreasing sequence which is bounded above is convergent. Therefore, this statement is say 3. Third statement. Therefore, from 1, 2 and 3, 1, 2 and 3, sequence Sn n is equal to 1 to infinity is convergent. Sequence Sn n is equal to 1 to infinity is convergent. Therefore, by definition of convergent series, convergent series, given series 1 plus 1 upon 2 factorial plus 1 upon 4 factorial plus 1 upon 6 factorial plus and so on converges. Hence the solution of the problem.